Our next presentation comes from one of our sponsors, DDN, Jean-Thomas Acquaviva. It's going to be talking about HPC distributed storage systems and using SKA as a new example. So welcome and thank you.
Okay, thanks a lot for the introduction. So my name is Jean-Thomas. I'm working for DDN since 10 years. A bit more actually. And today I'm going to talk mostly about a project which is somewhat my pet project. So SKA, the Square Kilometer Array. I started to work on this one in 2016. So it's kind of a long-term project. We learn a lot during this journey. So let's see. Okay, so what is this Square Kilometer Array? So here I feel a bit at odd because I know that there is some very good radio astronomer or astrophysicists in the room. So I'm going to be a bit careful. I'm more on the right side, right side, more on the IT part. So there is this square kilometer covered with antenna. They are capturing a lot of signal from the sky. So it's a huge acquisition device. And this signal are processed in order to produce science on this HPC grade system. So each of them is a range of exaflop or a bit lower. So it's serious HPC coupled with massive data acquisition infrastructure. So I saw this line from the University of Lausanne in Switzerland, EPFL. So just to give you some numbers, so it's, I would say, lot of zero for each of these numbers. So there is two sites, one in South Africa, one in Australia. So it's two sites where basically there are antennas. So here we need to process the data and we will generate scientific product, and then we need to bring this data back all over the world. So there is also a notion of distribution of data to different regional centers which are going to also make science out of this pre-processed data which have been pre-processed locally. So it's not only acquisition, it's not only pre-processing, it's also distribution. This project is, a long-time project, so there is a lot of uncertainties. And if you have to build the infrastructure, even just the IT part, not the antennas themselves, we need to basically try to reduce this cone of uncertainties in order to deliver possible technological scenario for the implementation. So the first issue is that the scale is massive. Even if the community has built Pathfinder, so there is some similar site in terms of processing. Nothing is of the same scale at the moment, so the SKA will be really unique by its dimension. So there is, of course, as we know in HPC, there is a scaling factor which is always bringing a lot of issues. Because it's long term, one of the specific problems that we have in the IT world is that we have a fast evolving ecosystem, right? So when I started to work on this project 8 years ago, the ecosystem was completely different from a technological standpoint than today. So we have to deal with GPU, CPU, so what is the best processing vehicle to do this signal processing? Should we store on solid state drive, which were quite new 8 years ago but are not commodity? Or should we keep hard drive which are very good properties? What will be the network technology? So it's kind of complicated because maybe in 5 years it will be also different again. And also from a scientific standpoint, these guys, they hope to make discovery. I hope for them, and I guess they hope as well. So it means that what they will try to look to extract out of the signal from the antenna may be different tomorrow from what they are doing today. So we can expect that the workload may change over time. So we have to be sure that the solution that we will provide will be somehow robust enough to accommodate innovation from the scientific community. And of course, on the software side, nothing is really sedimented. So as an example, I saw this slide from a guy in Italy, Claudio Gehler, a very nice fellow from INAF, working on SKA. So he took some of the key numerical kernels which are important for the radio astronomer, and he tried to look what are the performance that he can get out of different processing, using different parallelization schemes, using different languages. So at the end you have a very large array of possible implementation. On us as IT people, we have to provide the best solution. So what the SKAO did is that they set up a co-design team. So the idea, there is a lot of uncertainties, there is a lot of possible scenarios, let's do co-design. So the idea is that we'll try to find something which will mitigate the risk. So it's a very sane in terms of project management. And even if we improve the efficiency of the total system by few percent, considering the size of the system, I mean, the cost of this co-design project is extremely low, so we will have a very good return on investment. So I would say in terms of project management, it's quite sane. The team itself, so it's named Raccoon. I don't know why, but so I put a nice picture of a raccoon on the top of an antenna. Thanks, GenAI. And the idea is to yes. So the idea is to focus on the IT part, of course, because we have no skill outside of IT on HPC. And the focus is on storage. Why? Because from an IT standpoint, so sorry for my dear friend, radio astronomer, we see this project as a big acquisition device, and then we do storage, right? So, of course, because there is co-design, you have radio astronomers that teach us a lot of things that we do not know and we have sometimes a hard time to understand. It's a very complicated from a scientific standpoint. And it's not symmetrical in the sense that most of the time the physicists are pretty well slick and proficient in terms of IT. So I don't understand the equation, but they understand what I'm doing. However, we have a bit of secret sauce. So, for instance, what we did in this framework is that we organized some technical workshop, and we train, I don't know, but let's say we show what we can do. So here we use a darshan, and we spend like one day explaining to the scientists how they can capture and understand the I/O pattern of their application. So then we can have a good idea of what would be the best way to basically manage data and optimize code for them. And it's quite important in the sense, since the software stack is evolving, we can routinely, profile and try to see what is the impact in terms of I/O behavior. Okay, so why DDN is part of this team? Okay, first is that we are an actor which is well known to be at scale, so we have some nice system out there. So there is a couple that we are pretty proud of. So Cambridge, because it's in the UK, right? And also this big system, AI system within NVIDIA. So NVIDIA is operating multiple clusters for their research purpose, and the largest one is actually a DDN system. And also, maybe it's a bit more subtle, is that we are an open source company. So our key product is based on Leicester, which is an open source file system. So you see that here on the pie chart, we are, I would say, the largest contributor in terms of line of code and commits. Nevertheless, the project itself, so the Leicester file system, the blue line, the number of developers, so there is roughly 100 persons working on this file system, not all from one cloud, not all from DDN, because you see the number of organizations working on Leicester, so the red line, there are, like, I would say, roughly speaking, 12 to 20 different organizations working on Leicester. We take this open source file system, we industrialize it, and we sell it as a product in the name of Exascaler. Because we have this open source mindset, means that we are, I would say, by design, open to collaboration. So we are an actor in this ecosystem, European and a bit larger as well. So it means that we are running European project, Horizon 2020 or Horizon Europe today, or Euro HPC. We did some stuff in the UK with Excalibur as well. We have some initiative in the US. We just kick off a nice AI thing with Riken in Japan. So as an actor, we are pretty open to the community, so it means that we are well suited to do this co-design project. Now, if we look at basically all these big antenna in terms of storage, what are the key numbers? So every day, they are going to acquire around 40 petabytes of raw data, process them, and then produce around 2 petabytes of scientific data. So something which is clean and more meaningful for the next stage of the scientific utilization. So 2 petabytes per day. At the end of the year, you have 700 petabytes of data, and you don't want to throw them because they are very precious. So they are observational data which has been processed. So there is a lot of effort and money behind this data. So we need to keep them in an archive. and we need to be able to expose this archive to the remainder of the world, so people can cooperate and use it. Of course, the sky never stops, so it means that you need to be able to process your data on a 24-hour or 24-hour every day. And the community is very adamant about managing power. I don't know if it's for operational cost purpose or because these people are very conscious about, the implication of spending too much power. But each of these systems in Australia and South Africa, if I remember correctly, is in the framework of 2 megawatts. So it's a small envelope if you look at today's HPC system. So we have this idea that we have this different node, different workload. Some will have to be highly prioritized to process the acquisitional data, exactly like in weather forecast, but you still need to be able to make room for research applications. So we need to be able to maintain a good cohabitation between research application and the production application. So we end up with something like this, okay, so we have 40 petabytes, we want to have a bit of laxity here, so we have 50 petabytes of hot data, we have 1 terabyte of ingestion per second. Every day we need to produce 2 petabytes out of the 50 petabytes, so we have this 50 petabyte cold data, and then ultimately it will percolate into the large tape archive. And we need also to expose this data to the scientific community in Europe and all over the world. So here we are working with some specialists, I would say, in this topic, which is CERN, which is used to distribute data from their large particle accelerator. So we have a project with Ruscio, independently from this co-design things. We are working with the Ruscio team in CERN for the metadata catalog. Okay, so interestingly enough, this architecture, inner ring, outer ring, where the inner ring is about data production and the outer ring is more about data management and data publication, it's something which is making its way in the AI data center. So this is an architecture that we are seeing more and more, where you need to have a very fast storage in order to feed the GPU, or let's say the processing part. But the results, they need to be distributed, and then it's a different problematic. It's not about performance, it's about labeling, management, notifying potential subscribers that new data are available, avoiding duplication, allowing query. So it's really two different worlds. It's not just about performance. Okay, of course, we have in-house what you need to do this. So one specificity of DDN as a vendor is that we can accommodate a full array of different technology in our system. So it could be like fast flash, high-end, or it could be like more capacity flash, we name QLC, cheaper, good compromise, or it could be hard drive. With this hard drive, they still have very good, interesting properties actually. So you should not just say that it's all junk. There is a niche of application for hard drive, and you can mix this in order to build an architecture. Okay, at the end, everything fits in these 2U units. And this is not just hardware, there is a lot of software into this, there is a lot of virtualization in order to have everything in a single box. So if I have 2 boxes, I will have twice the performance, twice the capabilities, without needing to, every 2 boxes I need to add a switch or something like this. So there is a nice scalability factor out there. So here is an example. So I put many boxes on, it's scaled linearly, that's very nice. At the end, we run out of switch bandwidth, but so if we had a larger switch in the lab, we could have a better data, actually, better performance. So just a small point related to the storage substrate, so hard drive versus flash. So here it's about power. So this device, they have different power consumption if they are idle or if they are in operation. So here I took some hard drive and NVMe, and I plot the power consumption when they are in operation. And you see that the capacity is increasing. And there is 2 bumps. So the blue one here at the right here, and it's related to NVMe. So basically, the NVMe is more power greedy than hard drive. So if I have a strong power constraint, maybe NVMe is not the right solution. I should go for hard drive. Now, if the system is idle, what you can see is that my NVMe, which is very bad when there is a lot of activity, is not too bad when it's cold, if I can say so. So here, this plot somehow hints that we should go for something based on hard drive for SKA. However, there is always a bit more complexity out there. So if you look at the table on the right, it's when there is data movement. So if I need to move 1 terabyte out of my device, with a flash system, I can do this in few seconds. With a hard drive, I will need to operate full speed during minutes. And at the end, if I look at the number of watts needed to move 1 terabyte of data out of my device, it happens that my NVMe Gen 5 or PCI, right, is basically 2 orders of magnitude faster than more efficient than the hard drive. So finding the right substrate is maybe not as obvious as we can see. So we have to understand the workload to see what will be basically the pressure in terms of data movement in order to pick the most relevant, the most efficient technology for my system. Okay, one slide, I've already hinted about it, so this notion of data and metadata, it will be true, of course, for SKA, because this is acquisition device, so you need to tag a lot of things on your data. The time, of course, what part of the skies, what was a lot of instrumental version, even information. You can also include as metadata some kind of thumbnail version of what are the data. So at the end, this notion of data and metadata is a bit more blurry, and this is what we're observing also in other fields of the industry. So for example, if you look at annotated video, which are used commonly today for self-driving vehicle, for instance, every frame is annotated with a lot of metadata, and at the end, in number of bytes, the difference between data and metadata become a bit questionable. So again, I want to emphasize that we are working with this guy at CERN in order to see how we can accelerate or maybe intricate a bit together this metadata catalog ratio with all file system. Okay, we are still evolving. So here I took AC24 on the numbers because it's not GA yet, it will be announced at supercomputing. So the box that I showed you previously in the slide, there is a new generation, like IT every year or every 2 years we upgrade or things. So it will be, of course, faster and more capacitive than the current one. And I guess this is my last slide, and this is the most complicated part because this is a video. I don't know how can I play it. No? Oh yes, it works. Okay. So the blue guy here is my boss, and this guy maybe you know him, but he says that we are good. Okay, that's kind of it.